Good morning, all of you. Today, we are going to discuss about the line charge. Whenever charge is in the form of a thin line, it is said to be a line charge. The best example is electron beam in a CRO. How do we describe this line charge? The line charge is described with the term line charge density. It is represented by rho L, and the units are going to be coulombs per meter. The meaning of this one is, if I consider 1 meter length of the line charge, it contains a charge of rho L coulombs. If I consider 2 meter length, then the charge is going to be 2 into rho L. If I consider a differential length dl, how much charge it contains? Rho L into dl. So the differential charge in a differential length is given by dq is equal to rho L into dl. Suppose you have a line charge of some finite length. What is the total charge? Total charge q is equal to integral dq, that means integral rho L dl. So now let us find out the electric field intensity due to a line charge. Say I have a line charge of some length. The density is rho L coulombs per meter. At point P, we are required to find out the electric field intensity due to a line charge. So what we can do is, just now we have discussed in our previous lecture that both force and electric field intensity are vector quantities and linear quantities, in the sense that suppose there is a point charge of q1 here and another charge q2 here. At point P, if you want to find out what is the total electric field, so I need to consider these two charges q1, find out how much electric field it produces at point P, let that be E1. Then you consider q2, let E2 is electric field intensity produced by q2 at point P. Then what is the total electric field? E1 plus E2. So this is the total electric field. So this linearity property can be obtained in finding the electric field intensity due to a line charge. It is something like, suppose you have a line charge of some length. At this point, you have to find out what is the electric field intensity. I can divide this line charge into small segments. Let us say each of length dl. This length is dl, this length is dl, like that. So if I consider one such differential length dl, forget about the remaining part of the line charge. So differential length dl, how much charge it contains? dq is equal to rho L into dl, assuming that the line charge density is rho L coulombs per meter. So if you forget about the remaining part of the line charge, concentrate on this dl, which has a charge of rho L into dl. By all means, you consider this dq, rho L into dl, as a point charge. Let us say from here to here the distance is r1. What is the corresponding differential electric field? Let this is indicated with dE1. So dE1 is the differential electric field intensity at point P because of this dl, which carries a charge of rho L into dl. So what is the expression? Rho L into dl, you can always treat this as a point charge. So rho L into dl by 4 pi epsilon naught r1 square, and this is the direction. Next you take another dl, find out what is the electric field, dE2. Another dl, find out what is the electric field, dE3. Like that, the total electric field dE is equal to DE1 plus DE2 plus DE3, so on. So what exactly we are doing is we are dividing the line charge into small segments, and due to each differential length, we are finding out what is the electric field intensity at point P, and we are adding all these differential electric field intensities to get the total electric field intensity. So now, how are we going to implement this mathematically? Let us come back here. Now there is a line charge of density rho L coulombs per meter. At a given point P, we are required to find out what is electric field intensity. It is given that the perpendicular distance from point P onto this line charge is h, and it is making angles of alpha 1 and alpha 2 with the ends of the line charge. Assume that the line charge is placed along x-axis and this is y-axis. Point P lies in xy plane. So once you assume that point P lies in xy plane, all these lines which I have indicated here, the line joining point P to one end of the line charge, similarly point P to the other end of the line charge, this H, all these three lines lie in the xy plane. Now, in order to obtain the total electric field intensity, what I am going to do is, let me consider a differential length dx. Now, because it is placed along x-axis, I can represent the differential length as dx. In general, we represent this as dl. But in this case, because it is placed along x-axis, I can represent the differential length as dx. At a distance of x meters from one end of the line charge, consider a differential length dx. Let r is the distance from dx to point P, and this angle is theta. So when I consider a differential length dx, how much charge it contains? Rho L into dx. So if d is the electric field intensity at point P, differential electric field intensity at point P, because of this dx, which carries the charge of rho L into dx, what is the expression for dE? What is the expression for dE? dE is equal to rho L into dx by 4 pi epsilon naught r square. And this is the direction of dE. So if point P lies on the xy plane, all these lines, including R and even this dE, also lies in xy plane. It means that this dE has got two components, x component and y component. And if I define this angle as theta, what is dEx? dE cos theta. What is dEy? dE sin theta. So what is dEx? dE rho L into dx by 4 pi epsilon naught r square into cos theta. So this dEx is the differential x component of electric field at point P because of the differential length dx. So if I want to find out what is the total x component, I need to integrate this one. Rho L by 4 pi epsilon naught integral cos theta dx by r square. Now we need to integrate in such a way that the entire line charge is included. Okay. Here, as it is, we cannot perform the integration because if we want to perform the integration, there has to be only one variable. Here, theta is a variable. When we go from one end to the other end of the line chart, here theta is equal to alpha 1. Here this is theta. At this point, what is theta? 90 degrees. At this point, what is theta? 180 minus alpha 2. So theta is variable. What about x? X is also variable. Here x is equal to 0. For example, if L is the length of the line charge, x is equal to L here. So when you go from one end to the other end of the line charge, X is also variable. Then R is also variable. R is what? The distance from the differential length dx to point P. So if I consider this as dx, now this is my R. So R is varying from, when you go from one point to another point, R also varies. So we got three variables. X is variable, theta is variable, and R is also variable. So if you want to perform the integration, there has to be only one variable. So what we can do is, if we can represent this dx and r square in terms of theta, then there will be only one variable. You can integrate that expression. So for this, what I'm going to do is, as long as point P is fixed, from point P the perpendicular distance onto the line chart, this point also will be fixed. From here to here, from here to here, this distance is also constant. Let that distance is L1. Once point P is fixed, L1 is also fixed. If this is L1, this is X. So this distance is going to be L1 minus X. This angle is theta. So what is cot theta? Cot theta is equal to L1 minus X divided by H. So L1 minus X is equal to H cot theta. If I differentiate both sides, minus dx is equal to H into minus cosecant square theta d theta. That means dx is equal to H cosecant square theta d theta. So what exactly we have done is, this dx is represented in terms of theta. Like that, if r square is also represented in terms of theta, then our job is done. So from the same triangle, what is cosecant theta? Cosecant theta is equal to r by h. So what is r? H cosecant theta. Okay. So let us go back here. Integral cos theta into dx. What is dx? H cosecant square theta into d theta by r square. What is r? H cosecant theta whole square. So we get this as rho L by 4 pi epsilon naught H integral cos theta d theta. Now you can integrate this because there is only one variable theta. What are the limits of theta? We have to go from one end to the other end of the line chart. At this end, theta is equal to alpha 1. So we are measuring theta in the anti-clockwise direction. When theta is equal to alpha 1, we get one end of the line chart. When theta is equal to this one, 180 minus alpha 2, we get the other end. So the limits of theta would be alpha 1 to 180 minus alpha 2. So Ex is equal to rho L by 4 pi epsilon naught H sin alpha 2 minus sin alpha 1. On the same lines, we can find out Ey also. Ey is equal to rho L by 4 pi epsilon naught H cos alpha 1 plus cos alpha 2. Now let us discuss a few cases here. Suppose if point P lies along the perpendicular bisector of the line chart, that means alpha 1 will always be equal to alpha 2. You take any point along the perpendicular bisector, alpha 1 will always be equal to alpha 2. So what is x component? Rho L by 4 pi epsilon naught h sin alpha 2 minus sin alpha 1. If alpha 1 is equal to alpha 2, Ex would be 0. What about Ey? Rho L by 4 pi epsilon naught h cos alpha 1 plus cos alpha 2. Because alpha 2 is equal to alpha 1. So this is 2 cos alpha 1. So you will have only the normal component. Okay. Case 2. If the length of the line charge is infinite, now you can see that if you keep on increasing the length, what happens to the angles alpha 1 and alpha 2? Both alpha 1 and alpha 2 would be reduced. So finally, if the length is infinite, alpha 1 and alpha 2 both would be 0. That means Ex is equal to 0, Ey is equal to rho L by 4 pi epsilon naught h cos 0 plus cos 0, that means 2. So it is rho L by 4 pi epsilon naught h into 2. So this is the expression rho L by 2 pi epsilon naught h. So for an infinite length line charge, you have only y component of electric field. There is no x component. And one more point is, see, the x and y directions are the assigned directions. Finally, we got Ex as rho L by 4 pi epsilon naught h sin alpha 2 minus sin alpha 1. Similarly, Ey is equal to rho L by 4 pi epsilon naught h cos alpha 1 plus cos alpha 2. Because x and y are the assigned directions, suppose if I name this as y axis, this as z axis, then what happens? Now Ey would be equal to rho L by 4 pi epsilon naught h sin alpha 2 minus sin alpha 1. Ez would be, you would be getting cos alpha 1 plus cos alpha 2 term. So don't remember these expressions as Ex and Ey. Rather, you need to remember them as what is x component, parallel component, horizontal to the line charge. What is y component, normal to the line charge. So, horizontal component, you get sin alpha 2 minus sin alpha 1, and the normal component means you get cos alpha 1 plus cos alpha 2. Next. So, in these expressions, for the horizontal component or the normal component, if h is having some value, then only we are supposed to make use of these equations. What exactly I mean is, suppose you have a line charge of some length L, the density is rho L coulombs per meter. Okay. If point P lies in the same line as the line charge is placed along x-axis, point P is also placed along x-axis. Then what is the value of h? H is equal to 0. Then rho L by 4 pi epsilon naught h. So once h is 0, Ex would be infinity, Ey would be infinity. So which is incorrect. So these expressions Ex and Ey which we have derived are going to be applicable only if point P lies above the line charge. That means h is not 0. If point P lies in the same line as the line charge, we need to obtain the electric field intensity separately. Now let us discuss this case also. At point P, you are supposed to determine the electric field intensity, which is at a distance of h meters from one end of the line charge. Okay, let L is the total length of the line charge. In fact, the procedure is going to be same. I'm going to divide this line charge into small segments. Each length is differential length is, let us say, dx, and due to each dx, which is a charge of rho L into dx, we can find out what is the differential electric field at point P. So when I add all these differential electric field intensities, I get the total electric field intensity. But how do we proceed? How do we exactly carry out this operation mathematically? What we are going to do is, because we know that integration is nothing but summation, at a distance of x meters from one end, let me consider a differential length dx. And it has got a charge of rho L into dx. If dE is the electric field intensity at point P, because of this dx, what is this expression? dE is equal to rho L into dx. From here to here, what is the distance? L minus x plus h. L minus x plus h whole square. So rho L into dx by 4 pi epsilon naught L minus x plus h whole square. What is the direction? This is the direction of electric field. Remember that whenever there is an ambiguity in finding the direction of the electric field, you place 1 coulomb of positive charge and find out the direction of the force it experiences. For example, at point P, we are trying to find out the electric field intensity. Here there is a point charge rho L into dx. So this rho L into dx will try to push 1 coulomb of positive charge in this direction, because electric field intensity is nothing but force on a unit positive charge. So this is the direction of the force. What is this direction x? So dEx is given by rho L into dx by 4 pi epsilon naught L minus x plus h whole square. So what is Ex? Rho L by 4 pi epsilon naught integral dx by L minus x plus h whole square. Now I can straight away integrate this because there is only one variable x. L is constant, h is also constant. So it is equal to rho L by 4 pi epsilon naught 1 by L minus x plus h. What are the limits? X is equal to 0 to x is equal to L. So now this is the expression for the electric field intensity. Okay, in the next class, we are going to discuss how to determine the electric field intensity in cylindrical coordinates if the length of the line charge is infinite.